In this module, we will continue our discussion of mathematical models for physical systems. Specifically, we will review the first type of model which we introduced, which was the differential equation, and how we use the Laplace transform to solve differential equations. We will then introduce an alternative mathematical model called the transfer function, and we will also introduce a graphical model called the black diagram, which we have briefly seen previously. Recall that one of the reasons we like the Laplace transform is because it converts linear, time-invariant differential equations into algebraic equations, where in general we prefer to deal with algebraic equations rather than using calculus. One approach we found for solving differential equations was the direct method, where we directly found the solution x of t in terms of the particular solution and the homogeneous solution. The alternative is to take this other route, where we start with a differential equation, take the Laplace transform to transform it into an algebraic equation, solve that algebraic equation, and then use the inverse Laplace transform to take us back to the time domain in order to find the time-based solution, which is ultimately what we want. Here is an example to refresh us on the approach. This is similar to an example we've seen previously, except for the forcing function is a little different. The first step in this process is to take the Laplace transform of the differential equation. The Laplace transform of a time derivative becomes multiplication by s in the Laplace domain, if you recall. If you don't, you can look back at your notes for various properties, or you can look back in your book. This is the multiplication by s. There's also another term due to the initial condition, which in this case we are told is equal to 6. We can split the Laplace transform over addition, so then we take the Laplace transform of the next term, where the 3 is just a constant and it comes out front. The Laplace transform of x of t is simply x of s. And then we take the Laplace transform of a sine function, which again we can look back at our tables. Here is the entry for sine, where in this case our sine function is 2 times t, so omega is equal to 2. So we would expect a solution of 2 divided by s squared plus 2 squared. So using that property, that completes the Laplace transform of the differential equation. The next step is to solve this algebraic equation for x of s. Here we have a -6, which we can add to the right hand side. We're then left with s times x of s and 3 times x of s. We have a common factor of x of s that we can factor out, leaving us with the quantity s plus 3. Then to isolate x of s, we can divide through by s plus 3, giving us this final expression. Looking at the previous step, this 6 comes from the initial condition, and this term comes from the forcing sine input. And so the two terms of x of s can be thought of as the response of the system to the input and the response of the system to the initial condition. Furthermore, we can look at the poles of the system in order to better understand or predict the resulting time-based function. Recall that poles are solutions that make the denominator equal to 0. So if we got a common denominator, we would have an s squared plus 2 squared in the denominator and a quantity s plus 3 in the denominator, giving us poles of -3 and plus or minus 2j. The -3 is the root of the characteristic equation. It represents, in essence, the natural response of the system, the homogeneous solution. These complex poles represent the particular solution, and they're due to the forcing input coming from this sine wave. The third step is then to take the inverse Laplace transform in order to find the time-based function x of t. Looking at this expression, we can split this expression over the addition based on the properties of the Laplace transform. The second term is quite simple to address. It has the form of 1 over s plus a, which we can find readily in our table. This function we might not be able to find in our table directly. So here is the form of 1 over s plus a, and so that will have the form of an exponential, but there's nothing that's a quadratic term multiplying a linear term in the denominator. So what we can do is we can split this function into two parts, in essence using what we call the partial fraction expansion, which is basically the reverse of finding a common denominator. So we split this so that we have one term with a denominator of s plus 3 and another term with a denominator of s squared plus 2 squared. Doing this puts these into a form that we can recognize in our table. At this point, don't worry about where the numerators came from, where the values of the numerators came from. We will address that momentarily. So looking at this as a whole, we have two terms that are s plus 3, so we can combine those together. Here we have a denominator of s squared plus 2 squared, which is particular to sine functions and cosine functions. Again, looking at our table, a sine function will have a numerator that's just a constant. A cosine function will have a numerator which is s. So we can split this into a term with an s in the numerator and a term with a constant in the numerator. So these two added together gives us the last term. Here we'll split these guys. The s term, this constant will just come out front, giving us this term. In this case, we'll have a constant for the second term, but in order to match the form in the table, we don't want just a constant, we want a 2. So what we do is, in essence, we multiply 2 and divide by 2, which is the same as multiplying by 1, so it doesn't change anything, but it gives us the form that we were looking for, omega over s squared plus omega squared, simply multiplying a constant. So at this point, we have rearranged it into a form where we can recognize each of the terms in our Laplace transform pairs table. The constant comes out front. The inverse Laplace transform of this term is a cosine, where the omega is 2, so it's cosine 2t. Then we have another constant which just comes out front. The inverse Laplace transform of this term has the form of sine omega t, where the omega is again 2. This constant comes out front, and this has the form of 1 over s plus a, where a is equal to 3. Looking at our table, the inverse Laplace transform is e to the minus at, with here is our a. We again make the assumption that our time-based functions don't begin until t is greater than 0. We don't address negative time, and so this is our final solution. Recalling what our poles were, the poles were minus 3 and plus or minus 2j. The negative 3 was completely real, corresponding to exponential decay with no oscillation since it had no imaginary part. It was the root. Negative 3 was also the root of the characteristic equation, so this part is the homogeneous solution. We also had a forcing function that was a sinusoid of frequency 2, and so the particular solution has the same form as the forcing function. So again, this sine and cosine of the same frequency will give us a sinusoid of frequency 2, and it corresponds to the poles plus or minus 2j, where a complex or an imaginary portion of the pole tells us the frequency of oscillation, and the fact that it had a real part equal to 0 means that it neither decays nor grows. In the previous example, we saw how we needed to use something called a partial fraction expansion in order to get our Laplace transformed function into a form we could recognize in our tables. The idea of the partial fraction is to split rational functions into simpler terms. It's basically the reverse of finding a common denominator. The process of finding a partial fraction expansion has three different cases. One is when we have complex roots, or in other words, a quadratic that cannot be factored into real roots. When we have this form, which is the form we had in the previous example, the simple root will have a numerator that's just a constant. The quadratic denominator will have a numerator that's a linear function, b times s plus c in this case. We can also express this by factoring this s squared plus 4 into its factors, a part with negative 2j and a part with positive 2j. This is an example of what we will call case 1. Case 1 is when we have simple roots that are distinct. So in the previous case we had, for example, a root of plus 2j and a root of minus 2j. In this case we have two distinct roots of minus 1 and minus 2. As was the case that we showed previously, the numerators are just simple constants. When we have repeated roots, for example here it's as if we have two roots at minus 2, the form of the partial fraction expansion is slightly different. In addition to having a constant over s plus 2, we also will have a constant over s plus 2 squared. If we had even higher order roots, for example, if this was s plus 2 to the cubed, then we would additionally have a term with the denominator of s plus 2 cubed. In general, we will want to sort of memorize these three cases so that we know the form of the expansion, or we know what to expect. In general, we can perform this expansion by hand or using MATLAB. We will not perform any solutions by hand in this lecture, but we will address some simpler cases in subsequent lectures. At this point, I will introduce MATLAB for those of you that aren't very familiar, or it's been a while since you've used MATLAB. And in particular, I will introduce how to use MATLAB to perform the partial fraction expansion. The first example that we'll do is this example with a quadratic denominator. If you find the poles of this expression, or find the roots of the denominator, you'll find that the roots are minus 1 and minus 2. So there's two distinct real poles, and we can factor the denominator like this. And so think back to the three different cases of partial fraction expansion we introduced, and think about which one this is and what the form of the expansion will look like. Since the roots are real and distinct, this is what we will call type 1, and we can split the rational expression into two terms where each term will have a constant numerator. We will now use MATLAB in order to perform the expansion. For those of you that aren't familiar, just to give you a little bit of the lay of the land, over here on the left we have the files that are in the current folder. This is the current directory that we're in. Over on the right we have the workspace where various variables that we create will show up, and then here we have a command history which will list the different commands we've entered. In the middle is the command window, which is a command line interface where we will enter commands that call various MATLAB functions to do things for us. The very first kind of command that we'll introduce is how to define the Laplace variable s, which MATLAB can recognize. And so once we've done that, we can multiply it, we can divide it, etc., in order to express various Laplace domain functions. Looking back to the previous example that we had, our function had a numerator of 3 times s plus 2, where multiplication in MATLAB is expressed with the asterisk. And then the denominator we show with division as a backslash was s squared plus 3 times s plus 2. Exponents are defined using the caret, or this little hat. Hitting enter, we've defined a Laplace function g. If you have trouble keeping up with what I'm doing in this video, I will also post a transcript of the various commands and the output that's generated by MATLAB as we go along. So that's something else you can refer to in addition to the video. If you recall, one of the first things that we needed to do with our Laplace function was to determine what the poles were so that we would know how to factor the denominator. And one way to do that is to use the pole command, which shows us that the poles are -2 and -1, just like we found. Alternatively, we can use a roots command to find the roots of a polynomial, and what we do is we feed it a vector of coefficients of the polynomial, starting from the highest power moving to the left. So in this case, our highest power, s squared, the denominator, has a coefficient of 1. The next power has a coefficient of 3, and the constant term was just 2. If we had any terms that were missing, for example, if we just had s squared plus 2, then the coefficient in front of the s term is simply 0, and we need to include that 0. Hitting enter, again, we get what the roots of the denominator are. Now we will go ahead and show how to use the residue function. What the residue function is going to generate is 3 elements, r, p, and k. So r represents the residues, which are the constants in the numerator. So for our previous example, it will be the a and the b. The p are the poles, and the k is a gain, which in general we won't have to deal with. The only time that k is important is if you have a function where the numerator is a higher order than the denominator. In practice, that's a non-causal function. No physical system, physically realizable system, will have that form. So in general, we won't have to deal with that. The command itself is the residue command, and we feed it a vector b and a vector a, shown here, where b is the coefficients of the numerator and a is the coefficients of the denominator. So our numerator was 3s plus 2, so we will feed it a vector with 3 and 2. The denominator was a vector, well, it has coefficients of 1, 3, and 2. And so if we hit enter, we get the residues and the poles. And the ordering of those two vectors show the correspondence. So the first residue was 4, and that goes with the first pole, which was -2. And the second residue was -1, and that goes with the second pole, which was -1. Going back to our PowerPoint presentation, the residue that went with our pole at -1 was -1, and the residue that went with our pole at -2 was 4. So that's how we use MATLAB to find those numerators. Now we will look at our second example. This is the example that was part of the differential equation that we solved previously. Looking at this example, think back to which of the 3 cases this is. Here we have a quadratic term in the denominator which can't be factored into real roots. So either we can think of it as case 3, where we keep the quadratic term in the denominator, or we can think of it as case 1, where we factor it into 2 complex roots. If we expanded the denominator, if we multiplied it out, this is the form we would get. If we factored it into distinct roots, it would be like case 1, and all the numerators would be constants. If we did it as case 3, where we leave the denominator in the form of a quadratic, then the numerator won't simply be a constant, it will be a term that's linear in S. When we employ MATLAB, the form of the solution will be given in this form, case 1. So we will get 3 residues A, B, and C. But we can again use MATLAB to rearrange it back into this form. So going back to MATLAB, over here we can see the workspace has all of the quantities that we've defined so far. Also, the command history shows everything that we've done so far. Here I'm going to define a new transfer function. We had a numerator of 2. We had a denominator with a term of s plus 3 multiplying the quantity s squared plus 2 squared. And MATLAB recognizes again that s is the Laplace variable s. It performs all of the operations of multiplication, division, etc. to give us the expanded form of the denominator. We can then use the residue function. If I up arrow, I can cycle through all of my previous commands, and so I can get back to the residue command that I used earlier, except now our numerator and our denominator have different coefficients. The numerator is just a constant 2. The denominator is a third order system where the leading coefficient is 1. The s squared term has a coefficient of 3, the s term has a coefficient of 4, and the constant term is 12. If I hit enter, I get 3 residues, where again the ordering of the elements corresponds to the poles. So this residue corresponds to the factor s plus 3. These other 2 factors correspond to the plus 2j and the minus 2j, where MATLAB uses I for the imaginary number instead of j. I would actually like to put this back into the quadratic form. So I basically want to find a common denominator for the factors with roots of plus 2j and minus 2j. In order to do that, I can use the residue function. And so basically I can reverse the order. Instead of feeding it two inputs, which are the vectors representing the coefficients of the numerator and the denominator, I can feed it r, p, and k, and it'll spit back out the numerator and the denominator. So on the left I'll have the numerator and the denominator variables. I'll use the residue function, and I'll feed it r, p, and k. I actually don't want to feed it all 3 residues and all 3 poles, however, because the pole and the residue that goes with the pole at minus 3 is already factored out. I don't want to recombine it, but I do want to combine the last 2. And so this is 3 elements in the vector, and I'm going to choose the last 2 elements. So the colon is sort of it means like 2. I want to take element 2 through 3 of the residue vector, and I want to take element 2 through 3 of the pole vector. And if I do that, I get my numerator and my denominator. And I can use the TF command to rewrite that as an actual rational function in terms of s. In this case, so these coefficients in the numerator are the ones that I used in the previous example, so they should maybe look familiar. The denominator is s squared plus 4. The s term has a very small non-zero value, and that's basically just due to round-off error. So the denominator in reality is s squared plus 4. Before we jump back to the PowerPoint presentation, if you ever need some help using any of these MATLAB commands, you can always type help with the command and it'll give some information about the syntax and how to use it. You can also do DOC, and that'll open up basically kind of a web page that gives more details. While we have MATLAB open, let me go ahead and give you a few more tips about how to do plotting and things like that in MATLAB. So if you go back to your PowerPoint presentation, you can use this slide for some note-taking if you'd like, but again, I will post the script of our MATLAB session to help you. So let's go ahead and generate a vector representing time. So if I generate something like this, what this is going to do is it's going to generate an array from 0 to 4 in steps of 1. So it'll generate an array 0, 1, 2, 3, 4. Here I want to create a vector representing time, and I'm going to go from 0 to 2 seconds, and I'm going to go in steps of 0.01 seconds. This array will be quite large. If I just hit enter right now, it'll output the whole thing to the workspace, but I don't need to do that, so I'm going to put a semicolon following that to inhibit the return. And so now it's stored all of that. It's created this array T, as you can see over here in the workspace, but it didn't actually output it in the command window. So it goes from 0 to 2 in steps of 0.1. So it'll go 0 will be the first element of T, 0.1 will be the second element, 0.2, 0.3, 0.4, and so on. I now want to create a function that's basically the solution of the differential equation we found earlier. So we had a constant 6.1538 multiplying a decaying exponential, if you recall. The way that we write an exponential, or the natural number e, is with the MATLAB function exp, and its denominator, or its exponent, was -3 times t, where we again use the asterisk for multiplication. We then had a term for a cosine with a coefficient of negative 0.1538, cosine of 2t, and then we had a coefficient of 0.2307 multiplying the sine term. Again, I will put the semicolon, but this x will have the same number of elements as t, where it's basically evaluated at all 201 values of t that have been defined. So over here I can see I've created a vector of values for x. I can then plot these using the plot command, where I give it the first element is the horizontal axis, the second element corresponds to the vertical axis, and you can see what we get. We have this decaying exponential, and there's also, if we kept going, you would see the sinusoidal portion of it. let me now create another function that's a decaying sinusoid. So this is something that we saw as many physical systems have response like this. So I'll have, let's say, the same constant, 6.1538, have the same decaying exponential, but then I'm going to multiply it by a sine wave. Let's say that the sine wave has a frequency of 15 radians per second. When I hit enter, I'm going to get an error. And the reason that I get an error is because this exponential is essentially an array of 200 elements, and this sine also is an array of 200 elements, where each element of the array is that sine function evaluated at the different values of t. So the first element is the value when t is 0, the second element is the value when t is 0.1, the third element is when t is 0.2, and so on. And so if you're multiplying two arrays, MATLAB is presuming that you want to do matrix multiplication, and so a 1 by n array cannot be multiplied by a 1 by n array. The matrix multiplication won't work. In that case, really what you're intending to do is to multiply a row by a column. In this case, however, we don't want to do matrix multiplication. We want to multiply element by element. We want to multiply the exponent when t is equal to 0 times the sine wave when t is equal to 0. That'll be our first element. Then we want to do the multiplication when t is 0.1 and t is 0.1, and so on. And so the way that you represent element by element operations is to add a period before the asterisk. So dot asterisk means element by element multiplication. Again, I'll put the semicolon to inhibit the returning of the output to the command line. Now I will plot the two functions on top of each other. So I'll plot my first function versus t, and I will plot my second function versus t. By doing that, by giving it 4 elements, it will presume that the first two are an x and y pair, and the second two are also an x and y pair. And if I plot them, you'll see the two graphs, and it'll by default choose the line type. But I can change the line type if I'd like. I can specify that the second function be in red, and instead of being a solid line, it could be a dashed line. I can also add a title, so whatever I want it to be. I could also add a legend to identify which function each of the lines go with. So the first function that I gave it was the x function, the second function I gave it was the y function. I can also label the axes using x label for the y label, or for the horizontal label, and y label for the vertical. Going back and looking, you can see all of the different elements that we've added to our figure. In general, quite a lot of what we'll do in this class will require plotting. So these basic functions are something that you should try to become familiar with. Now returning back to the PowerPoint presentation, we will now introduce an alternative model to the differential equation that we introduced earlier. As has been sort of demonstrated, is that sometimes we want to remain in the Laplace domain because the mathematical operations can be easier. For example, differential equations become algebraic equations. This is going to be shown in further detail as we go along here. Therefore, it's useful to be able to model a physical system in terms of its Laplace transformed function. In particular, the transfer function is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input, and it assumes zero initial conditions. So this is the general form we'll call g of s, the transfer function, i.e. our system. For example, it could be an electric motor, and u is the input and y is the output, so u could perhaps be voltage and y perhaps could be speed. So that's the general form. Transfer functions in general characterize the input-output relationship of a dynamic system without taking into account the effective initial conditions. So it just characterizes the response of y in response to u. Transfer functions are a property of the system itself. It doesn't depend on the type of forcing input. Transfer functions have units, but do not provide information concerning the physical structure of a system. They only apply to linear time invariant systems because you cannot take a Laplace transform of a nonlinear function of time. And they make combining systems very easy. So each of these aspects of a transfer function won't necessarily be apparent at this point, but I will try and point them out as we go through some examples. So the approach that we're going to use for finding a transfer function is as follows. Transfer functions are found from differential equations. So we, for example, could derive the differential equation model from first principles and then transform it into transfer function form. First, we need to identify what is the input and what is the output. In this case, let's go ahead and say that y is the output and u is the input. In general, this is sort of a design decision. We could define a transfer function where the speed is the output, or we could define a transfer function where the acceleration is the output. It just depends on sort of our point of view, what it is that we are considering as designers. We then take the Laplace transform of the differential equation, assuming zero initial conditions. So we basically take the Laplace transform of this whole differential equation. If we started with the first term and you looked back in your Laplace transform properties tables, the constant will come out front. A third derivative in the time domain becomes multiplication by x cubed in the Laplace domain, and then you also have additional terms due to the initial conditions. So s squared times the initial condition of y in the time domain minus s times y dot of 0, the initial velocity condition, minus y double dot of 0. So that's the most general form of that property, but since we're assuming zero initial conditions, all of these terms go away. Therefore, when we take the Laplace transform, we'll end up with an s cubed term for the third derivative, an s squared term for the second derivative, an s term, and so on, giving us something of this form. The final step is to rearrange that expression into the form of a transfer function, which is output over input. Looking at the left, our output is y of s. We can factor y of s out of that whole side, leaving y of s multiplying a polynomial a0 s cubed plus a1 s squared plus a2s plus a3. On the right hand side, we have our input u of s, which we can all factor out. Also factor out, we can divide u of s to the left in order to get output over input, and we can divide the polynomial in terms of the a coefficients to the right to give us this form. So this is our transfer function output divided by input. Looking at another example, this differential equation we have derived previously representing a drive line. It says find the transfer function for the following, where t of t is the input and theta of t is the output. So again, this is a design decision, and it's the first step in the process to define what is the input and what is the output. So that's been done for us. We're defining the torque being applied to the one end of the drive line as the input, and the sort of twist or displacement of the one end of the drive line as being the output. Again, that's a design decision. The second step is to take the Laplace transform of the differential equation. Since we're assuming the initial conditions are 0, when we take the Laplace transform of theta double dot, we will just get s squared times theta of s. Our first derivative will become multiplication by s. Laplace transform of theta will become theta of s, and the Laplace transform of t will become t of s. The third step is then to rearrange this into the form output over input. So on the left we can factor out theta of s, leaving us with a polynomial js squared plus bs plus k. You can divide t of s to the left, divide the polynomial to the right, and that gives us the form of our transfer function output over input. And so looking at this, we notice a few things. One, it doesn't depend on the forcing input at all. This represents the drive line no matter what type of input torque we have. This is what the drive line looks like, whether or not the torque is applied in a step, whether the torque is applied sinusoidally. So the transfer function doesn't depend on the forcing input, the form of the forcing input. We can also see that since we assumed 0 initial conditions, it doesn't capture the effective initial conditions on the system. And the transfer function does have units, where the units are the units of the output divided by the units of the input. We'll just make an assumption, say that the angular displacement or the angular twist is defined in radians, and let's say the torque is defined in newton meters. And so these are the units of the transfer function, but they don't necessarily tell us anything about the internal structure of the system. So we don't necessarily know what the coefficients in the various polynomials mean, what they physically represent, unless we derived it from first principles. So that is the resulting transfer function for this example. It's also important to note that we're unable to take the Laplace transform of nonlinear functions of time. So all of these thetas are theta of t, and so if this differential equation would have had theta dot squared or sine of theta of t or anything like that, we would not have been able to represent the system as a transfer function. Another form of model that's important is a block diagram. And oftentimes a transfer function like this can be represented as a block diagram as shown. Here, g of s is our system, and it's represented as a block. And u of s and y of s are signals, where u of s is the input to our system and y of s is the output of our system. So for example, g of s could be a drive line, where the input is the torque applied to the one end of the drive line, and y of s is the angular twist in the drive line. Mathematically, the output is equal to the transfer function times the input, and you can see that sort of here. We can just divide or multiply u of s on both sides to the left hand side. And so mathematically this is very simple. It's a very simple way to calculate the output signal. It's the transfer function multiplied by the input signal. If we were in the time domain, we would need to use the convolution integral, which is much more difficult than just simple multiplication. The advantage of this becomes especially apparent when we start to combine systems. So let's say, for example, we have two systems in series. So for example, g of s could represent some power electronics, and h of s could represent an electric motor, or g of s could represent an IC engine, and h of s could represent the drive line, whatever. Recognizing that the output of h of s is going to be the input multiplying the transfer function, we can see that the output signal just has that form, where we already knew that y of s had that form. And so if we wanted to know what the sort of combined dynamics of these two systems in series were, an IC engine in series with a driveline, where u of s is the input to both systems in series, and this is the output of both systems in series, we can see that we basically just multiply the two transfer functions. And so this begins to give us some understanding of how nicely the transfer function is for combining complicated systems. Multiplying two transfer functions is much simpler than performing a bunch of convolution integrals. We've seen block diagrams previously when we first introduced the structure of a control system, and here you can see again it's useful for visualizing very complex systems, lots of components put together with lots of inputs and outputs to the system. In a situation like this, each of those blocks, each of those systems can be represented as a transfer function, and each of the arrows represents signal flow. And we can start to get a sense of how nicely we can combine these individual subsystems into one large system model. If these were all differential equations, it would be much more challenging. A couple of other elements of a block diagram that I'll take a second to explain is one, these summing junctions. So for example, this summing junction, the signal coming in on the positive sign is our reference R, and the signal coming in on the negative sign is our measured output y sub m. And so E sub m is then the positive signal subtracting the signal coming in on the negative sign. So that's what this summing junction represents. Also, we have this branching point, and anywhere that a line is branched off, the signal is unchanged. So the output of the whole block diagram is y, and where we branch it off, this signal is also y. We will come back to block diagrams later in the semester. We will now introduce the concept of time response. And so by time response, I mean when we have a model of a physical system, we in essence want to determine the response of its output as a function of time. When we had differential equation models, we were able to do this basically just by solving the differential equation. We can also do this with transfer function models. So consider the transfer function of our driveline from earlier, where we had an input of torque and an output of angular twist. In general, we may want to determine the twist experienced by a driveline for different types of torque inputs. For example, if there's a big sudden application of torque, a step in torque, or if the torque is being oscillated at some frequency. And so the way that we find that, theta of t, is first to find theta of s. And we can find theta of s where the output is just the transfer function multiplying the input. And then we take the inverse Laplace transform of theta of s to get the corresponding time function theta of t. So let's go ahead and do that for a couple of standard inputs. First, let's consider an impulse input. So we're finding the impulse response of the driveline. So you could consider this to be a very rapid sort of spike on the torque, where it's a large torque for a short duration of time. Theta of s, the output signal again, is the transfer function times the input signal. G of s is defined on the previous slide, 1 over js squared plus bs plus k. T of s is the Laplace transform of the unit impulse. If we look back at our Laplace transform table, the Laplace transform of a unit impulse is just equal to 1. So we substitute in our expression for t of s and g of s, and that gives us the expression for theta of s. I'm going to go ahead and substitute some numbers for j, b, and k in order to make things a little bit easier. So let's assume that our expression for theta of s has that form. If we looked at the poles of this transfer function, the roots of the denominator, we would find that they're complex. So we would expect that our time function, when we take the inverse Laplace transform, would be a decaying sinusoid. The real part of the poles tells us the rate of decay or growth. The imaginary part of the pole tells us the frequency of oscillation. And so again, we've dealt with this a little bit before. We've seen some similar examples, and so we would expect something like this form, where we perform where we complete the square. So we take the 6 and divide by 2 to get 3. If we expanded this, we would get s squared plus 6s plus 9. So we have the term matching the s squared, we have the term matching the 6s, but we don't want 9, we want 25. And so in order to get 25, we need to add 16 more, which is 4 squared. Looking at this, you may remember that it has a similar form to a sine, where a sine is omega over s squared plus omega squared, but the shift in the Laplace domain corresponds to multiplication by an exponential in the time domain. But in order to get the form that we want, we need this coefficient to match this coefficient. So in order to get a 4 in the numerator, we need to factor out a 25. Then if we do that, we can recognize this from our Laplace transform pairs table and our Laplace transform properties tables. The 25 comes out front. The shift by 3 corresponds to e to the minus 3t, and the remainder is sine of 4t, because 4 corresponds to the omega. So what this tells us is, if there's an impulsive torque applied to the driveline, we would expect it to ring. The angular twist in the driveline would oscillate with decaying amplitude. Now let's look at how the driveline would respond to a different type of torque input, in this case a step in torque. So a very rapid application of torque that's held. Again, the output signal is equal to the transfer function times the input signal. Looking back at our Laplace transform table, the Laplace transform of a unit step is equal to 1 over s. So we take the Laplace transform of the unit step, we get 1 over s, we plug in for g of s and t of s to get this form. If we looked in our table, we wouldn't find an expression that looks like this. But what we can do is we can perform a partial fraction expansion, like we did earlier with MATLAB. We get numerators as shown. Here again, so the second term is easily recognized as a step being multiplied by 4. Here we have this denominator that's representative of a sinusoid, either a sine wave or a cosine wave. For a sine, we would like to have a numerator of omega, which is 4. For a cosine, we would like to have a numerator of s, where the s has been shifted by 3. So we're going to end up with something like this, where the first term is a decaying cosine, the second term is a decaying sine, and the last term is a step. In order to get the correct coefficients here, we need a coefficient of minus 4 in terms of s. So if we choose a to be minus 4, that gives us the right coefficient. Distributing that negative 4 will give us a minus 12. We don't want a negative 12, we want a negative 24. So in order to get a negative 24, we need this to be negative 12. 4 multiplying negative 3 gives us negative 12. And that expansion is equal to the original function. We again can take the inverse Laplace transform. The -4 comes out front. This is a cosine with frequency 4 and a exponential decay of -3 shown there. Here we have a sine with a frequency of 4 and also a decaying exponential of e to the -3t, constant of -3 out front. This is 4 times a unit step, which we could represent as 4 times the function 1 of t. But since we make the presumption that our function doesn't start until time greater than or equal to 0, we can also just represent it as a constant 4. And so that time function shows the response of the drive line. Therefore, if we applied a large step in torque to one end of the drive line, we would expect the twist in the drive line to oscillate with decaying amplitude, but also reach a steady state value that's non-zero. So, which physically makes sense. That torque applied on the one end will cause the drive line to twist, and it won't return to its original undeformed shape. So as t goes to infinity, this will die out to 0, and we'll be left with some twist. We will now go and return back to MATLAB and show a couple of MATLAB commands for determining time response of a system. So here's MATLAB again. We still have all of the commands from previously. I'm going to go ahead and clear all of that text to make things cleaner. We still have the Laplace variable s defined. I will go ahead and define our transfer function g, which was 100 divided by s squared plus 6 times s plus 25. To find the impulse response, we can use the impulse command. So we use the command impulse and supply it a transfer function g, and it'll generate a graph of the corresponding output for that, for an input that's a unit impulse. So that's what it looks like, which is what we would expect. It's a decaying sinusoid that decays to 0 as time goes to infinity. Similarly, we can find the step response of our transfer function by using the step command. For this, we saw that the output should be a decaying sinusoid with an offset of 4 added to it. And that's exactly what we found. Returning back to the PowerPoint presentation, that concludes Module 5. In summary, we learned what a partial fraction expansion was. It's a means to expand a rational function into individual terms such that we can recognize the Laplace transformed function in our set of tables. In general, there are 3 different cases: when we have real distinct roots, when we have repeated roots, and when we have complex roots and we don't factor the quadratic. We can perform this partial fraction expansion by hand or with MATLAB. In this module, we use MATLAB. In the future, we will learn how to do this by hand for simple cases. We learned an alternative mathematical representation of physical systems called the transfer function. The transfer function is in the Laplace domain. It represents the input-output behavior of a system. It has pros and cons compared to a differential equation representation. For example, it makes it very easy to combine different models, different subsystems. It's a completely algebraic model, which is nice. Disadvantages are that it doesn't capture the initial conditions of the system, and that it could only be applied to linear time invariant models. We also introduced block diagrams as a graphical representation of complex systems, and we introduced the concept of finding a time response of a system, i.e. finding the output of a system as a function of time when given a transfer function model and the input to the system.